Our first three lemmas about the study of the structures of those notions we defined at the beginning. And starting from the lemma 4, we'll get into the core part of the proof, namely the counting. And we'll realize this general idea of the proof gradually, which we talked about at the beginning. Now, given an admissible matrix Y, we let M of Y to be the number of matrices that are nilpotent and nil commute with Y. So let me write down, this is the number of nilpotent matrices that nil commute with Y. And if 0 or O is the zero matrix, then M of O is the number of all nilpotent matrices, which is what we want to find. And here's our lemma 4. Our lemma 4 states that if you sum up M of Y's over all possible admissible matrices Y, you get Q raised to power n times M of O. And now let's prove this. We start with the right hand side. Q raised to power n times M of O. This, by our definition, is Q raised to power n times the number of all nilpotent matrices, which is the number of nil sub n of Fq. And this Q raised to power n by our lemma 3 is equal to the number of elements in alpha. So here we used lemma 3, part 2. So now let's look at the product of those two cardinalities. Here's the key observation. For each nilpotent matrix A, since the cardinality of alpha A is equal to Q raised to power n, by lemma 3, that's statement number 2, they are precisely Q raised to power n many distinct Y's that nil commute with A. And if you translate this into mathematical notations, this is the same as saying that this product can be written into the following sum. The summation over A taken from the set of all nilpotent matrices, or for each A, you consider all y's in alpha A, meaning that y nil commutes with A. And the summands are all ones. So by the remark in this blue, this product of cardinalities will be same as this sum. So why are we interested to write this guy as this double sum? It should be like a mathematical instinct for you to see that whenever we have a double sum, we always want to switch the order of summation, which looks like some sort of finite Frobenius theorem. So in this double sum, we consider for each A that's nilpotent, the summation of all y's in LA of those ones. We count the number of y's in alpha. Now how about we start with y's and we count how many a's that nil commutes with y. So now let me carefully write this down. So you get this double sum. This, if you combine A and Y as a pair in the Cartesian product. So if you look at the pair A, Y in the Cartesian product of nilpotent matrices over FQ and script A, where Y is in alpha, and you sum up those ones. Namely, you count how many pairs are there satisfying those relations. And this will be equal to the summation over all pairs still in this Cartesian product such that ny is equal to ya. And this last term gives you, if you consider for each y in the union of all those alpha a's, it's A nilpotent. You sum over those ones over all b's in the set of nilpotent matrices over FQ such that ny is equal to yb. So here I should use another letter because we have already used A in here. And now you look at this guy. Is this something familiar to you? Have you seen this before? You should, because this guy is precisely over m of y. Do you see it? If you don't, let me replace this A by B now. So now we are really playing with the letter B. This m of y is precisely the number of nilpotent b's that nil commutes with y. So this part is precisely m of y. And this first sum is really just a summation over all possible y's that are admissible. This is precisely the definition of admissible matrices. And this is our left-hand side, which finishes the proof of our lemma 4. And now let's look at the statement of lemma 4 again. You notice that this M of O also appears on the left-hand side of this equation. So, because our final goal is to compute the number M of O, you might want to move M of O on the left-hand side to the right. So now let me rewrite this as follows. So lemma 4 is the same as saying the summation of all those admissible y's that are non-zero of M of y is equal to q raised to the power n minus 1 times M of O. And this is q to the nth power minus 1 times the number of nilpotent matrices over f sub q. So, in order to count this guy, it suffices to compute this sum. What we will do next is that we are going to grade this by the rank of the matrices Y that are admissible. So let me write this down. We will grade this by rank of Y's, which will be reflected in our next lemma, the lemma 5.